we need to learn how to use multiple linear regression in order to create useful models with it. So when we do this, how do we decide? How do we choose which of our variables at hand to actually include in our model? Should we use all of them or some of them, or how does that work? So if we have a set, we got a bunch of these input X predictors, and then we got our Y that we want to do that. The thing is, no matter, we can always fit a model to it. You feed a bunch of X's and a Y into R, and it will always give you slopes and an intercept. It will always give you a slope for each predictor, but that doesn't necessarily mean that every single one of those are actually useful, that actually have a statistically significant relationship, that actually tells us anything helpful. And so there are times when we can get a better model by getting rid of some of our X input predictor variables. So that's kind of what we're going to look at today. How do we get the most useful model possible? So first, we need to reconsider R squared. So remember, R squared tells us the percentage of the variation in Y, our output response variable, that can be accounted for by our linear model. So if we study that just by itself, our multiple R squared, what we find is that every time you add another X column, another predictor variable into the model, it never goes down. Least it could do is just stay fixed, and it almost always goes up. And it does that even if the new variable isn't really helpful, doesn't have a statistically significant relationship, it doesn't do anything useful at all. So we need something better. So what we statistics people do is we take our R squared and we adjust it to account for the number of variables going in there. And so that if we add another variable that doesn't do anything, that doesn't help, then our adjusted R squared will actually go down. And that gives us a criteria. It gives us a number. I can look at that adjusted R squared and see as it goes up or it goes down, I can decide whether or not adding a variable actually helps me, produces a more useful model. So let's consider this one. Suppose we go back to this data on loans, and let's make a model based on 5 predictors. So again, look at here, we've got summary LM, loans interest rate is the thing we want to predict. We want to predict the interest rate charged for a loan. And we have 5 input factors: the number of inquiries in the last 12 months into a person's credit score, their debt to income ratio, their employment length, how many years they can get a job, the total number of credit lines the person has, the open number of credit lines the person has. We feed all this in there, and holy cow, look at that. We have a model. We have an intercept, and we have 5 different slopes. And then for each one of those, we have a p-value, and then we've got an adjusted R squared, and ooh, look at those p-values. Most of them are very statistically significant, less than -16th. Look at that last one. 0.7927 is the p-value on the number of open credit lines. That's not statistically significant. It says if my null hypothesis is that the actual slope is 0, and I just randomly choose a bunch of numbers, what's the probability I would get something as big as that slope I got? And they say the probability is 0.7927, which is very large, certainly larger than any reasonable value of alpha, certainly bigger than 0.05. Well, that's interesting. Okay, so once again, here's our model. Our model says interest rate equals the intercept, 11.79, plus the first slope times the inquiries in the last 12 months, and the next slope times the next variable. Okay, we can add all these up. There's our model. But that p-value on the number of open credit lines is terrible. All right, also look, notice that the adjusted R squared value is 0.04851. What if we cut that one out? What if we prune that one from our model, and we, instead of having 5 predictors, we only use the first 4? What happens? The model gets better. Look at that. So now all the p-values are at least decent, and that p-value is now the adjusted R squared on this one. The adjusted R squared is 0.04861. It actually went up. We cut out one of our variables, and it got better. And so based on this, we can say that, yeah, we have a better model. Those 4 variables do a better job at predicting what the interest rate is going to be than the 5 variables did. That's an interesting and useful thing. So our goal is to make a model, to take a whole bunch of potential X input variables and choose which ones we're going to use to predict that. There are lots of ways to do that. There isn't any one right answer. Different people can use different strategies and come up with different models, different sets of variables. But in order to keep things systematic, we like to do that in the sciences. We like to do this in a systematic and predictable way. There are 2 main strategies that are used. First of all, there's what we call backwards elimination. In that case, you start out with all of them. The first thing I do is I put in every single one of the potential X variables. I do a fit, and then I look at what I get, and then gradually I remove variables, trying to improve the model, and I stop removing variables when I can't do that anymore. The other method is forward selection. In this case, we look at each variable individually and start with the most important one, and then gradually add variables to that until we can't improve the model by adding any more variables. So either backwards elimination or forward selection are a reasonable strategy, a reasonable thing to do. The criteria for choosing whether to include or not include a different variable, there are two different things we can do. We can base this on the adjusted R squared. If in this case, or if we want to make the adjusted R squared as large as possible. Usually, if our goal is to make accurate predictions, if I want to predict things as correctly as possible, then usually we work with adjusted R squared. On the other hand, if we're thinking statistical significance, which of these variables is connected to the response variable, and I want to find the statistically significant predictors, then another criteria that can be used is the p-value. Ending when we've got all the p-values below 0.05. We want them all to be statistically significant. And we're going to get different results depending on what we do. And that's okay. That's kind of a remarkable thing. We're in a math class, and yet there is not one true, right, correct answer. There's a little bit of a judgment call in here, and different strategies may lead us to different places. And that's just reality. The real world is big and messy and complicated, and we do not always understand all of it. So, quick summary. This adjusted R squared tells us whether or not, when we add another X variable, another predictor variable, whether that really improves the power of our model to predict the Y, the response variable. And we find that sometimes more is not better. Sometimes less is more, if you know what I mean. So sometimes fewer predictor variables will have a larger adjusted R squared. In which case, we got these two strategies. We can either do backwards elimination, starting with every single variable we've got and then gradually pruning them back until we've got the best possible model, or we can do forward selection, adding variables one at a time until we find any that improve the model, either based on the criteria of finding the largest possible adjusted R squared, or using p-values to decide whether to keep a variable or to discard it. And again, the big thing to emphasize here is that different people can get different results based on the strategy they employ. And that doesn't necessarily mean that one of them is wrong. We can get useful models that are slightly different in different ways. And so some knowledge and some thought and some judgment call is necessary in this vast aspect of things.